Hey everybody, I'm Fermin Redondo from Clemson University. My mentors were Mark Swiftdak and Jimmy Drake, and I'm back with yet another plasma physics and kinetics reconnection project. Woo! So I'll be talking about pickup ion acceleration. So let's start off with what magnetic reconnection is, because we've never heard of it. It's a pretty fun physical process in plasma, which for my intents and purposes will be a soup of protons and electrons, and I'll be calling the protons ions for this entire talk. But magnetic reconnection happens when opposing field lines, they kind of come together and merge, and they snap and go out like this, depositing a lot of stored magnetic field energy into plasma. And so I've given everyone the famous GIF here, but I also have this well-known ball of plasma called the sun. And magnetic reconnection happens in this corona. Here it's undergoing a coronal mass ejection. And so that's caused by magnetic reconnection, as given from Sonia's talk, and also happens in black holes, fusion plasmas. It's a pretty fun process. Now let me get into like what pickup ions and energetic neutrals are. So we have this thing called the heliosphere. It's like the sun's domain of influence. And throughout the entire heliosphere, the solar wind particles are going through charge exchange with the neutral interstellar medium. This will give you fast ions interacting with neutrals, which gives you pickup ions and energetic neutral atoms. These energetic neutrals are going at high speeds. And so there's a region of the heliosphere called the termination shock, where solar wind loses energy, becomes compressed, and reconnection is likely there. This will leave one for later. So I'm talking about a region called the heliotail. Let me show you a map of the heliosphere. This is a simulation of it. It's kind of shaped like a croissant. But just to give you an idea of the scale that we're working on here, this is where all of our solar system planets are. This is a 500 AU simulation. This right here, the colors, they're characteristic outgoing speed. It's plasma speed that I won't go into. But yeah, this is the heliotail. We don't have direct in situ data from it. What we know about what goes on in there, we kind of infer from other observations and theory. Like the Voyager probes, which actually going up this way, and probes like IBEX and Inca, which count energetic neutrals coming in. And this is more proof that reconnection happens. This is the solar current sheet. It's kind of shaped like a ballerina skirt. And it's compressed. It's got layers. It should be important for later. So we send these instruments out into the termination shock and collect measurements, and we modeled what we think should happen to the energetic neutrals. This should be like the energy spectra that we get. But then we get these observations, and this is a log plus. This is a huge discrepancy. There's what's going on here? I'm going to hypothesize that it could be reconnection happening in the heliotail, accelerating ions and giving us this energetic neutral flux that we did not expect. So they take the difference between these distributions and generate another distribution of ions. Well, with this distribution of ions, we can get the expected energetic flux. So just to make sure we're measuring energetic neutrals here, and we're measuring ions here. This is like my target. This is what I want to see. I want to see if magnetic reconnection can reproduce this ion distribution. And to that end, I use particle in a cell simulations, which we also have never heard of. It's kind of what it sounds like. You have a grid full of particles, and you impose upon this grid initial and boundary conditions. The geometry I'm using here is parallel current sheets. Current sheet is kind of what it sounds like. It's a sheet of current, and around it, use your right-hand rule. This is current pointing outwards in this simulation. You're going to see that the field lines are going to be oppositely oriented around it, and that's where reconnection happens. And so likely in the heliotail, this is the kind of geometry we're going to be seeing. So I chose to simulate it like that. Let me show you guys a quick little movie of it happening. And so this is electron current evolving until full reconnection. And throughout this project, I varied the simulations in scale, size, and parameters to see if I could get that distribution of ions. And so yeah, big simulations can give us density, magnetic field strength, current, and evolve it through time. So we solve Maxwell's equations, iterate through time. Pressure times, I can't let the whole movie continue. So from the PIC simulations, I can actually generate electron and ion velocity and energy distributions. And this is what we ended up getting if you include a non-negligible pickup ion population at the beginning of the simulations. As you can see, it has two humps like the earlier plot, meaning that magnetic reconnection is a plausible physical process driving ion acceleration and could possibly lead to those observed distributions that we saw. So further work will include making my distribution look more accurate, making it look like the initial plot shown, and furthermore, including it in the actual simulations to see the results. Like to shout out to Trend, Math Quantum, Grad Math, and Human Aerospace Group, and Daniel, my mentors, Jim Mark, and everyone else here for a great summer.